Hi, I'm Kelly Marquisio, and today I will be presenting work done on my internship at Meta AI entitled Mini Model Adaptation. This is joint work with Patrick Lewis, Yeong Chen, and Mikel Artecha. Large machine learning systems use a lot of energy and create carbon emissions. Exactly the cost is quite difficult to estimate, and there has been some disagreement as to how this measurement should be done. But most people would agree that training machine learning systems does use a lot of energy, and that making ML models smaller and use less energy is a worthy pursuit. I'm now going to describe one way of adapting large language models to new languages. In this standard method, you can first start out by pre-training a model in some source language. Here we pre-train the model in English. We can then train a new embedding layer in a second language while keeping the transformer body frozen. So we continue training here with the embedding layer unfrozen, reinitialized for the new language, and the body of the transformers frozen. So in this way, you're getting language-specific embeddings for your second language. You can then swap back in the English embeddings and freeze them and fine-tune the body of the model on some downstream task. And then you can plug in the embeddings trained for the second language earlier into this model and get zero-shot cross-lingual transfer to the new language. This is very exciting, but the problem with this is that it costs in the Roberta base model about 54 exaflops or about 21 GPU days if you were using a V100. Now, for large industry labs, perhaps this is not much of a problem, but certainly for academic users or individual users, this is going to become prohibitive. So in this paper, we wanted to know, can we adapt a large language model using only a fraction of its parameters? We call this method mini model adaptation. And again, here we're going to adapt this large model using only a small fraction of its parameters, but still be able to do zero-shot cross-lingual transfer at the end. In our first method, which we call MiniJoint, we jointly pre-train a primary model and a mini model using a secondary masked language modeling head attached at a shallow middle layer. So we attach the secondary head here, and we are going to train this model such that the loss is the average over the two heads. What's interesting here is that if you train the model in such a way, you actually have you can think of this as the fact that you have a small language model that can perform the language modeling task in its own right. And this smaller model lives inside a large language model that also can perform the language modeling task. So it's kind of like you have two complete language models, one of which lives inside the other and forms the first handful of layers of a large model. From there, we can extract the bottom layers of the model that are attached to the secondary head, recalling that itself was trained to be a fully functional language model. We can freeze those layers and train a new embedding layer in the second language upon that frozen mini model. And then the rest of the process continues as I showed you in the standard baseline. So we would have the frozen English embeddings, we would fine-tune the body of the transformer model on some downstream task, and then plug in the second language embeddings for zero-shot cross-lingual transfer. So the computational savings that we're looking at here is coming in this step 2, the target language embedding training, whereas before we had to train these embeddings upon the entire model, doing the full forwards and backwards pass, which was quite computationally expensive. Now we can just do the forwards and backwards pass over the smaller mini model, so we get quite a large computational savings. We have another method which we call MiniPost. In this one, you can start out with a pre-trained language model, so that you download off the internet. You can extract a small number of layers and add a few number of trainable parameters on top. You freeze the bottom of this model and continue to train it in the first language, so that's English here. So in that way, you're effectively closing the language model. You're extracting the bottom few layers, adding some trainable parameters, and continued training so that this actually works as a language model in its own right. From there, you can freeze those layers, and that then becomes your mini model upon which you can train the embeddings in the second language. So what we do in this paper is we are going to adapt to a new language, then we are going to observe NLP task performance, and we're going to count the flops. We choose languages that are meant to represent various language families in the world and also various writing systems. Here I'm showing you what we're going to call the language performance upper bound. So this is the baseline system that I showed before, where the model and the adaptation process uses the same height model throughout the entire procedure. As I told you, this takes about 20.9 GPU days to do the adaptation phase. We're going to call this the language performance upper bound because this is the standard method for doing adaptation. And what we're going to try to do in this paper is not exceed the baseline performance, but actually try to get as close to baseline performance as possible while using the minimal amount of flops. We also have a small baseline. So here we want to look at what can we do with a low amount of flops in the standard setup. So this is going to be the standard baseline setup where you have the model of consistent height throughout the entire procedure. So you're adapting on the full model, but we're just using a shorter model to save on computation. And this is going to be our language performance lower bound. Again, it's what can you do with a low amount of flops in the standard setup. MiniPost takes about 11.3 GPU days to train to completion, and MiniJoint takes about 8.1 days. You'll notice that MiniJoint uses the same amount of computation as the small baseline. This was done intentionally because the goal here is that we want to see, using the same amount of computation, but a different architecture that we've chosen for MiniJoint, how much better can we get than the standard baseline? So when you look at the results in the next few slides, I want you to focus on the difference between the small baseline and MiniJoint, because these use the same amount of flops, but MiniJoint has had an architectural change. And then I also want you to observe how close we can get to the full baseline performance using our mini model adaptation methods. The first task is cross-lingual natural language inference. Here you have two sentences and you want to label whether the second one is an entailment, a contradiction, or neutral. Our baseline scores a 72% accuracy on this task averaged across languages. The small baseline drops performance significantly to 66.3%. MiniPost scores a 71.2, and MiniJoint scores a 70.3. So you can see we have dropped a little bit in performance in comparison to the baseline, but you'll also notice that we used a lot less computation. Extractive question answering, MLQA. Here, given a context text and a question, the goal is to predict the answer span from that context. So the baseline scores a 56.9 F1 on MLQA. The small baseline scores 51.2. And MiniPost and MiniJoint almost entirely recover the performance of the baseline. Finally, paraphrase identification. Here you have two sentences and you just want to say whether these two are paraphrases of one another. The baseline scores an 83.4. The small baseline drops performance significantly to 74.5%. MiniPost scores 83.1, and MiniJoint actually achieves slightly better performance than the baseline despite using only about a third of the computation. Here is the training curve through the first GPU week. The motivation for this was, although we all might want to use the state-of-the-art NLP system at all times, if it's expensive to get there, potentially we're okay sacrificing a small amount of quality in order to build a system rapidly that works quite well in our language of choice. So we define that system that works good enough as scoring 95% of the baseline system's performance. And we define that 95% threshold as near maximal performance. You can see that threshold in the dotted blue line here. So what we're looking at here is we want to see, as we're training the system, when do we actually cross that 95% threshold for full baseline performance? And we'll see that although I told you it took about 21 GPU days for the baseline system to adapt, it turns out that if we average over languages, we can actually get to the 95% performance in only a little bit over 2 GPU days. And then if we look at MiniPost, we can see that it takes only a bit over 1 day to get to that 95% threshold. and MiniJoint is actually able to hit near maximal performance in less than a day. So whereas we were talking about adaptation being prohibitively expensive in previous slides, now your average user can adapt to their language of choice in only about a GPU day. Here is the average speed up of mini model adaptation over the baseline. So for this, we do the relative speed up per language, and then we average over languages. And you can see that depending on the architecture that we've done, either MiniPost in red or MiniJoint in yellow, we get between a 1.4x and a 2.9x speed up over the baseline. So what we've learned from this paper is that compute efficient multilingual adaptation is possible using only a fraction of a large model's parameters.